our next speaker is Andrew Johnston, and his talk is titled Nondeterminate Lines, Pathfinding Through Artificial Intelligence. Thank you.
It works. Thank you for the organizers for having me as a film and media studies scholar. I'm interested in a wonderful conversation, and I've learned a lot today, and so thank you so much. As many have noted at this symposium, the field of AI was established in the 1950s within the nascent discipline of cybernetics and focused on producing machine behaviors that took into account various programmed conditions and histories of action. One area of particular interest for these researchers was animation and the independent movement of forms across a visual grid, so one of the abstractions from the previous talk. In 1956, Edsger Dijkstra developed new programming protocols and algorithms that would enable a computational object to explore, through trial and error, a two-dimensional space until finding a pre-established goal. Moving from one node to another on a visual grid, Dijkstra set into motion an object whose intentions were determined, but whose pregnations were independent within set boundaries. So this is a sort of play on the traveling salesman problem. Through my presentation, I show how this rarely discussed pathfinding algorithm affected the history of digital animation and games, especially as it became a central component of AI bots. But it was also instrumental to the development of special effects software packages that produced swarms and other particles to interact with one another in films, such as the Lord of the Rings trilogy and I, Robot, as well as many others. Throughout my paper, I argue for positioning these AI bots as object engines that are not built around ideas of intelligence, but instead programmed animations across Euclidean space. This resituating reveals connections between programmers and engineers working in AI and moving image culture, especially through the ways in which they wish to model particular modes and aesthetic articulations found in animation. By placing these engines in this context, I hope to show how these technologies operate both as aesthetic and epistemic objects, whose actions, though created in the 1950s, were contoured by later algorithms, reinforcing a play of history in contemporary AI and animation pathfinding. To begin, I want to articulate the stakes for doing this project while grounding it within a clear technological and methodological framework, especially for the setting. First, I want to emphasize a problem-solution method of production-oriented analyses. By this, I mean that, perhaps more than is recognized, digital animations and technological systems are driven by trial and error. As different narrative or aesthetic goals are established by filmmakers and programmers, innovations and solutions often emerge from within these contexts. For example, a dominant mode of producing textural details within CGI environments came from the problems in the light cycle sequence of the 1982 Tron film. Noting that the CGI in Tron looked too smoothly rendered, Ken Perlin developed a way to introduce texture noise in CGI objects to make them appear more realistic, called Perlin noise, and earning him an Academy Award in the first for a CGI algorithm. This algorithm and its derivations are still used and function as a filter that introduces elements of noise into image pixels that can be controlled to, quote, create convincing representations of clouds, fire, water, stars, marble, wood, rock, soap films, and crystals. 2, the second stake centers on developing formal vocabularies of analysis for digital animations. Too often these are black boxed, and sometimes they are overly fetishized. In an expanded version of this text, I'm interested in working through the methodological tensions in materialist aesthetic analyses, or what Roland Barthes and Yves Bois calls formal materialism, while engaging with artworks and the effects forms of production has on them, setting into motion an analytic that focuses on the triangulation between technology, formal renderings found in the elements of art, line, shape, space, etc., and phenomenological experience. So this leads me to my third interest in working through this material, namely the epistemological stakes for doing so. By opening this black box of digital animation, We're also working through the changes between understandings of animation and technologies of motion that historically motivate animators over time. This is a point that animator Pierre Hébert makes when self-reflexively asking, what do I really do when I animate? Like other scholars and critics, Hébert struggles with what animation is, working through his thoughts about it in his own artistic practice. And like others, he argues that animation is intertwined with cinema's invention in the late 19th century out of a cultural and technological mix of photography and many optical toys and devices. But he emphasizes that this common point of origin takes on a different significance for various practices and communities of filmmaking. While the mechanical synthesis of photographic action in cinema stabilized into an almost taken for granted black box over its history of use, a similarly technical foundation did not emerge for animation. In fact, Hébert explains that, quote, on the contrary, animation is constantly reopening the technical black box. Some of its key elements, such as the very idea of reconstructing motion frame by frame, are contained in that black box. So every time an animator animates, she is potentially reactivating the memory of the moment in which the elements of cinema got together to form the tightly knitted entity that is live action cinema. Animation is based on a dissociative, disjunctive action inflicted upon the very structure of cinema. Animation sends cinema back to the moment just prior to cinema's very existence. So in this historiographic model, animation moves forward in time with different media ecologies and indexes technological and epistemological changes through its experiments. As technical syntheses change, so too does animation's operations and conceptual identity, even as it travels back to the very idea of technical syntheses of motion. So let's examine what for many seems to be the most opaque synthesis for digital animation, and then locate forms of action present within it and other systems by peeling back rendering layers. The swarms and crowds produced for special effects sequences generate wonder by utilizing a program whose own name, Massive, gestures towards obfuscation. Massive is short for Multiple Agent Simulation System in Virtual Environment, and generates the crowd swarms seen here by including thousands of animated figures simultaneously at once, or agents, each of whom move in the same sequenced loop, where articulations of arms, heads, legs, and torsos operate at the same speed over the same duration. What makes these figures seemingly distinct from one another in order to make the crowd appear realistic is one, there are only a few different physical classes present, which presents visual uniformity when required, and two, the loops of action are started at different times for each of the agents present. Rather than appearing as though the figures are running three-legged races in a long chain, their gaits are stepped across the formation in a large-scale rendering environment. But this compiled rendering is functionally working with each agent many times over, Massive. Paring this down to singular objects that operate like game NPCs reveals a bit more about the ways in which they are made to move and the AI that they use. Contemporary NPCs distinguish themselves through their image rendering and multiple heuristic systems. First, these images are illuminated through flat, Gouraud, or Phong shading, and the arenas that they are present within, often game engine environments, have pre-calculated light maps that help determine plays of value and shadow as objects interact with one another in that space, a technique used by many digital animations and made popular by Pixar's first film, Luxo Jr. These tessellated, shaded, and multi-textured characters with dynamic shadows are rasterized objects that interact with their environment and player in a way that is modeled off photographic renderings of three-dimensional space. Stripping them of this image detail, sometimes produced in rendering farms of computers at 24 hours per frame, leaves them with the heuristics and programmed actions that often justify their place in game or animation narratives. These are determined through a hierarchical system of goals specific to the object. In Massive or many other contemporary games, moving towards an endpoint, chasing particular classes in the programmed environment, or carrying out a specific action are all negotiated by the object through what is called a fuzzy logic, which is sorting through and calculating the relative weight of each goal within the animated environment in given circumstances, such as a player or another NPC entering and altering that space. The most common action and priority within the object's logic system is movement. For all the complexity found in three-dimensional games, objects within them move according to the same operations and programming functions as these familiar faces. PacMan ghosts, oh my, 5, move across a 224 by 288 pixel grid that for the game designers and iconic ghosts is defined more simply through a 28 by 36 tiled space. And just like NPCs in later games, the ghosts move through this grid via a pathfinding algorithm called A-star, an optimization of Dijkstra's earlier pathfinding program. Again, Dijkstra sought to develop an automated solution for finding the shortest path between 2 points. And to do so, he created an algorithm that examines a two-dimensional Euclidean grid and all the possible paths that are available between different nodes within that grid. To solve this map, calculations that add together the difficulty, sometimes measured by distance of travel between points in the map, are assessed through a flood fill summation. This means that all the possible movements from the starting point of the puzzle are valued, and that the chain of possible movements from each of the following nodes are then added to each previous possible movement, and so forth, with the reverse hierarchy of summations being updated as the fill continues until all possible routes are accounted for and added up. Like calculating the time of travel between different buildings or cities, this was used for routing network management and for mapping visual space and actions within it in a more general manner. The optimization of the search algorithm A-star was developed in 1967 to make the pathfinding actions more efficient. Rather than relying solely on inputted values of effort or action made between nodes on the map, A-star took into account the measured distance between points on the map or other heuristics that were programmed into the parameters of the path request. Notably, if A-star locates a shorter possible path between nodes through its if-then structure, then it will not examine possible paths that would generate a higher value than the path currently being assessed. And so this conditional logic made A-star the smart search version of Dijkstra's algorithm, a sort of projection of cognitive action similar to which Stephanie Dick IDs in the mid-20th century in a different context. And also, this proved long-lasting, as it is still used with added heuristics to take into account obstacles, other NPCs, or other goals. But the action along a vector of travel remains the same, guiding objects with varied graphical renderings in particular directions. This last point is important because it begins to, 1, orient an understanding of these animations around looped actions, and 2, explains how most visual AI functions through a similar if-then logical condition around particular goal-oriented actions, seen, for instance, in DeepMind's reinforcement learning neural network for Atari or StarCraft II. For our own part, if we return to the historiographic model discussed at the beginning of this talk, where animators are constantly opening that black box of technological motion at different historic junctions, the digital pathfinding algorithms that structure so much of the ubiquitous animation within contemporary media ecologies indexes the technological landscape of the current moment. Even lighting techniques within digital animation called ray tracing are beginning to use pathfinding algorithms to calculate the complicated actions of light in rendered space, as Disney explains in their video on the topic, Disney's Practical Guide to Path Tracing. Beginning at a virtual camera and ending at an artificial light source in the same space, the algorithmic light moves along a vector and bounces geometrically until finding the endpoint in the most efficient manner possible. Information about distance, objects, and the number of nodes encountered will determine value and color fills. There we go. Value and color fills for associated pixels along the path. With increased number of rays and faster GPUs, more information can be included in the scene, providing greater control over the desired aesthetic effect and ability to mimic codes of cinematic realism within animated sequences generated in real time. In this way, AI pathfinding algorithms are no longer limited to mapping action within Euclidean space, but also now help constitute that space. And like other technologies in the history of moving images, these will impact historicized notions of realism and aesthetic value as they become more ubiquitous. So let's examine once again the contour of that action in space. AI pathfinding relies on a formal and aesthetic force that is familiar to animators and others, the line. Often invoked through analyses of the hand of the animator trope that Donald Crafton wrote about years ago, which affords a privileged status to the animator over the moving creation. What is not often discussed is the technology that generates this element of art. As Bart explains in his analysis of Jackson Pollock's work, line, no matter how supple, light, or uncertain, always implies a force, a direction. It is energon work, and it displays the traces of its pulsation and self-consumption. Line is action become visible. With different technical instantiations of the line, there are different forces of aesthetic action and movement. Though animated bodies often hide their compositional renderings, lines of action trace their form and trail their bodies, constellating the legacy of abstraction and synthesis that produce animation generally, much like Etienne Jules Marais' chronophotographic snapshots of motion that break down bodily movement into vector paths. So a pathfinding line sometimes only appears as a trace of the action made through the directional force of the animated body. Occasionally, these can be anticipated, and sometimes an aesthetic pleasure in gaming is found through their surprise movements. But the algorithm guides the contours of the movement and marks the indeterminate force that articulates its operations. While aesthetic wonder and awe continue to drive so many discussions of AI's use within visual media environments, this is a demo of a new animation Unreal Engine from Epic. These systems emerge from mid-20th century technologies and practitioners of cybernetics, forcing us, like a Bears animators and these animators, to, quote, reactivate the memory of the movement in which the elements of computational paradigms emerged and open the black box of digital movement and animation from this time. Thanks.